No. So today we are going to discuss mainly the method of maximum likelihood, as you can see it in there. So try to recall what we did last time. So our problem, the main problem was of parameter estimation. What do I mean by parameter estimation? So you have a random variable that you are going to measure experimentally. I called it x, and you will not only going to measure it only once, but you would be measuring it n times. Okay, so you have the data, the data using which you will be estimating the parameter has n entries, n number of entries, and this n is a fixed number. And so this whole set of data, this n number of data, I define to be my data sample, and the whole thing constitutes my experiment. And this experiment, in theory, is repeatable. That means you can perform the experiment as many times as you want. Okay, but you have only performed it once, and based on that experimental data, you have to tell me what is the best guess of for an unknown parameter and of the theory. Now, I suppose these random numbers, this random number that you are measuring, let's say any x, okay, is distributed according to a distribution that I defined as fx, and it depends on a parameter that I call theta. Okay, so this random distribution depends on this parameter theta. There can be multiple parameters, of course, but just for the start, let us assume that there is only one parameter on which my PDF, my probability distribution, depends on. Okay. Now, and this theta you do not know a priori, and this theta you want to actually estimate. Okay. So so now actually you do the experiment. Now you do your experiment. By experiment means get the random number n times. So you have a set that is, let's say, x1, x2, up to xn. Now these are definite numbers. Okay, so these are no longer just a placeholder value. So this x1 might have a value, let's say 2.03 in some units. Okay, this x2 might have a value of 3.9. Okay, and you have this. Okay, so the same number are the same. Now, based on this number, so this based on this data, what is the best guess for theta? So the problem is based on these values, what is your best guess for theta? Okay. So of course, this theta that you are going to estimate, unless you do this experiment infinite times, you can never pin down the exact value of theta, the true value of theta. That is unknown. Okay. Now, based on this data, I am trying to guess this. I am trying to guess, or I am trying to estimate this parameter theta. So that estimate I call as theta hat. This is my estimate for theta. And if I have to estimate, so since these are numbers, I have to give a number for this theta hat as well. Okay. So this theta hat can only depend on this x1, x2, and xn. So this theta hat can only depend on x1, x2, xn, because these are the only things that I know. So these are the data that I know. So theta hat can only be a function of my data samples. Okay. Now, the crucial question is, so this far I can do generally. Now, the crucial question is, what is the functional dependence of this theta hat, the estimate for theta? Okay. remember, these two might be very different, okay, but our job is to, based on this limited information, I am giving you a guess, and that is my best guess for theta hat with some degree of uncertainty that we will discuss later. Okay, so this theta hat can be a function of x1, x2, and xn. Now the question is, what is the nature of this function? How do I know this function? Okay, in practical situation, how do I know how does theta hat depends on these known parameters? Okay. Now in the previous class, what we did is that for simple parameters, let's say mean and variance, okay, mean and standard deviation, for example, we could somehow guess what should be the dependence on x1, x2, dot, 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 xn of the unknown things that I want to estimate. For example, for mean, I started with my arithmetic mean, and I have shown that it is independent of the nature of the distribution. You can always give an estimate for the mean as the arithmetic average of your data sample. Okay. So irrespective of the nature of fx, you can always estimate the mean as the arithmetic average of your data sample. And I showed that estimator, like the general functional form that I called as my estimator, that estimator was first of all an unbiased estimator, okay, and it had the standard deviation for that estimator, like the statistical error for that estimator, is inversely proportional to the size of the data sample. It's inversely proportional to it. Okay. Similarly, we constructed the estimator for sigma square, is the variance of a distribution in general, without paying any attention to the nature of the distribution so far. And we also found out that we can also write the estimator for our variance as well, and so on. So these two we could guess, we could get away by guessing. Now, when it comes to more complicated things, so again, so this theta can be anything. Okay, now suppose in the experiment of, again, say Young's modulus measurement, you have this small tiny values of this strain. Let's say that there's tiny displacements that you have measured, and these tiny displacements, the relation of these tiny displacements with the weight that you put in depends on the Young's modulus of the material. Okay. So now this will be a bit complicated now. So for that you have to know what is the distribution of this x. So that depends on my Young's modulus. If this theta is my Young's modulus, then what is the best guess of my Young's modulus? So this is the kind of problem now I am trying to address. And now I am no longer considering the general distribution. We will assume that somehow this distribution is known, that how my random number is distributed. This can be known from Monte Carlo simulation and so far and so forth. So this is the general nature of this distribution is known as a parametric dependence on theta. So you basically you know the distribution of x as a parametric dependence on theta. That means you know how the distribution of x look like for any given value of theta on the continuous real number line. If theta is a real parameter. Okay. So you take so basically this is known. So basically you have simulated for, let's say, theta equals 1, 1.1, 1.2, and so on. All the values, these infinite values of theta, you know this distribution look like. Now when you have measured this thing x1, x2, xn, now you have to make a conclusion which theta value of the from this real number line best describes such an experimental outcome. That is my goal. That is the point I'm trying to make. Okay. Remember, in the previous class, I emphasized that this n number of data points, this x1, x2, xn, okay. So those things are independent measurements. Okay. So the value of x1 has nothing to do with value of x2 and so on and so forth. So first of all, let us figure out what is the joint probability of finding x1, x2, and dot 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 up to xn. Okay, and that is quite simply so. This is how it goes. So suppose you have observed it at x1. First of all, the first observable is at x1. Now you ask, what is the probability that I will find my x value between x1 to x1 plus dx1? And that would be given by, so P, probability of finding x at x1, that would be given by f x1 given theta times dx1, okay, between this interval. Okay. This is the probability, not the PDF anymore, because the total thing is the probability. Similarly, now you measure again x independently and you ask for the probability that you will get the value x2, and you will get between x2 and x2 plus dx2, and that would be given by f x2 theta dx2, okay, and so on. Now remember, these are sequential measurements of x. May not be sequential, but these are independent measurements of x. So the combined probability that I will observe x1 and then I will observe x2 and then I will observe x3 and so on. So the combined probability for to observe this data vector, okay, is the combination of all these probability. Since probability is multiplicative for independent events, then I can write the joint probability. Joint probability is basically the multiplication of all these things. So this is basically f x1 theta times f x2 given theta times so on up to f xn given theta, and then dx1 up to dxn. So then basically joint PDF, and so the joint PDF would be given by, you divide by the volume element, and the joint PDF is the multiplication of these PDFs. Okay, so f x1 theta, f x2 theta, and f xn theta. Okay, so this is my joint probability distribution function for this data. Now notice this thing. So here x1, x2, xn are numbers. Okay, so things that I have observed here, 2.03, 3.9, and so on and so forth. Now the only undetermined parameter here, the only thing that I do not know is a theta. So this whole thing that I have written here, the joint PDF, is a function of theta that I call as L theta. Okay. And this is my likelihood function. Okay. Now try to apply your intuition here. Okay. So this thing gives you the joint PDF of observing x1, x2, dot 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 to xn given the value of theta. Now, if my guess is very close to the true value of theta that produces this x1, x2 data, then this PDF will be high, the probability will be high, right? Because there is there is this hidden true value of theta that I do not know, but let's say God knows, that produces these let's say this array of data values x1, x2, dot, 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 up to xn. Okay. Now Now I am guessing the value of theta. I am just uh, calculating theta hat. I am scanning over all possible theta hat, all possible theta hat, and then if while scanning this all possible theta hat in the real number plane, if my guess becomes very close to the actual true value of theta that only God knows maybe, okay, then this probability will be very high because that is the value of theta that gave this distribution, this that hidden value of theta. So this joint PDF, the value of this will be maximum if my theta value is very close to the true theta value. Okay. Now, so basically, this is my definition. So the definition is that if I have del L theta del theta at some theta equals theta hat ml equals 0, so I am trying to figure out where my likelihood function becomes maximum, then I can then that value of theta gives me my maximum likelihood estimate for the value of theta. So this basically uh, gives the ML estimate for theta. Okay, and it is denoted by theta hat ML. That is means so theta hat means it is an estimator for theta, and the estimator is obtained using the maximum likelihood method. Okay, but this is the maximum likelihood estimate for theta. So what you will say? So you will say, see, I never know the true value of theta, of course, but given this data, I can say that my best guess for the possible value of this unknown parameter theta is this theta hat ml, where my likelihood function is maximized. And that I will quote as my best estimate for theta. Okay. Now, of course, this can be generalized if you have more than one parameter. If you have more than one parameter, then you just call it a theta vector. You have a number of parameters, so theta 1, theta 2, up to theta m, okay, and you have many parameters. So you basically maximize the likelihood function with respect to all those parameters. If you have, let's say, theta 1 and theta 2, and you say that is the best, that is the best value, that's the best fit value for my theta. So how you do it? So in essence, what you are doing is this. So basically, you are constructing a likelihood function, and using that likelihood function, you are maximizing the likelihood function with respect to your unknown parameter, and whenever that happens, you are quoting that as your likelihood as your maximum likelihood estimate. Now, very often it is more convenient to work with logarithm of likelihood because the likelihood is a multiplicative function. Okay. Taking the derivative of a multiplicative function might not be trivial always, but if I take the logarithm of this likelihood function, remember, since logarithm is a monotonically increasing function between, let's say, so this first of all, likelihood function is a positive definite, so I can safely take its logarithm, and the logarithm is also a monotonically increasing function. Okay, so if something maximizes my likelihood function, then it will also maximize my logarithm of the likelihood function. That is sometimes called the log likelihood. So the log likelihood is basically nothing but the ln of L theta. And instead of applying this, you just demand del theta of ln L theta at theta equals theta ml equals 0. Okay? In fact, to get a better visual appeal, if you actually plot the log of the likelihood function, suppose this is the theta, and this is ln of L theta, then it should look something like this. And you figure out the maximum. At some value of theta, it is a maximum. And that value is your best fit value. So ML best fit value for the log likelihood function. So if everybody understands this, now I will pause and take some questions if there are any at this point.
Sir,
Yes.
can there be more than one likelihood functions? I mean, likelihood values?
Well, if you mean if there are more than one maxima, then you take the global maximum.
Okay.
Okay.
Why did we go for the log? Why did we take the log of the likelihood function?
Because the likelihood function itself is a multiplicative function,
Yes.
and see, it's like in statistical mechanics. I don't know how many of you have read statistical mechanics that seriously, but if some of you did, then we start with number of microstates, right? And the logarithm of number of microstates gives me the entropy. Okay. So when we say that what is the equilibrium configuration in thermal equilibrium, to what configuration my system should approach, we can say it in two ways. The macro state that has the maximum number of microstate is the most stable one. So basically, you maximize the number of microstate under a given macrostate, and that is the emergent state. Okay, and that comes out to be the emergent state. But in practice, since number of microstate is a multiplicative quantity, okay, so you take the logarithm of that, logarithm of the number of microstate, and you maximize that, because the number of if the number of microstate is maximized, then logarithm of the number of microstate is also maximized. Then, and you call that logarithm to be your entropy, and you say that my most stable configuration is the configuration with maximum entropy. It's the same here.
Okay. Okay.
Yeah.
Sir,
Yes.
can you give an example where the probability distribution function depends upon two parameters like theta 1 and theta 2, and where we can apply that?
Yeah, yes. I will do that. I mean, I plan to do that thing as an exercise, but we will do it right now. I will give an example with one parameter first, and then two parameter. I will come to that.
Okay, thank you.
Yeah. So now let me come to this example. Again, the examples are from nuclear physics and so on and so forth. But if someone has any other ideas, please, you are welcome to give this thing. So the radioactive decay, again, so radioactive decay for, let's say, any radioactive substance, just for the lack of examples, let me call this thing as radium, okay, of radium, radiative decay of radium. Now, here, what is the problem? Let me first define the problem again. Okay, and people who are doing particle physics take this very seriously, because this is the bread and butter of particle physics experiment. How do you estimate your parameters? Again, people both with theory and experiments should pay attention to this. So the radioactive decay formula, fortunately, we know that the probability that a particular nucleus will decay within a time frame t. Okay. So the probability that a particular nucleus will decay within a time t, okay, and given the value tau for that, so this will give you the average lifetime, is given by 1 by tau e to the power minus t over tau. Okay. So this tau is the average lifetime. Let's say this tau is 5 microsecond. Suppose this tau. See, remember, ideally this tau you never know. God knows. Okay. So again, I am referencing God too many times, but only figuratively. So God created radium, and you see radium all around you, and you have observed the radium decays. Okay. Now, you also are pretty confident that the decay of radium can be described by this law. So this law is also well known. Okay. This is the law in which the radium decays. Now, the only thing you do not know, what is the value of tau for radium? Okay. So what is the value of tau for radium? This 5 microsecond, that only God knows, because God created radium, and at the time of creating radium, he or she has assigned a particular lifetime to this radium nuclei, and that is, let's say, 5 microsecond. That only God knows. You do not know that. Now, you are petty earthmen, okay? You are earth dwellers. So you see radium all over the world, and you take a small sample of this radium nuclei, okay, and you observe them decay. And every time a radium nucleus decays, it clicks. Some detector of you, it clicks. Okay? So radium decays into something and into a photon, and whenever my detector detects that photon, the detector clicks, and at that moment it records the time and it clicks every time. Now, whenever it clicks, it also records the time. So suppose you have observed the decay of 10 radium nuclei. 10 is just a number. Okay, don't take that very seriously. So, and every time it clicked, you recorded at what point that nuclei decayed. So you got this value. So T1 equals, let's say, 0.2 microsecond. T2 equals 0.9 microsecond. T3 equals 3 microsecond. Okay. T4 again 2.4 microsecond. Okay. And you have such values up to T10. So this you have observed. This you have observed. Now, based on this observation, you have to make a guess for this tau. Now, tau without the hat, that thing only God knows. So this, if I say tau without anything, then that thing is that thing basically reflects true value of tau. That only God knows. So based on these measurements, you can only conclude about tau hat, some tau hat that depends on this T1, T2, T10. You don't know how, and you just say that this is a close approximation of this tau. Now, how good an approximation this tau hat is for this tau that depends on many factors. One of the factor is the sample size, of course. Okay. Now, so this is what I'm going to do now. So I have measured this, and I am trying to estimate the value of tau. Everybody understands this problem? Everybody understands that?
Yes, sir.
Good. So now that we have a very good idea of what I am going to do. So again, the thing I laid out before you is first. So step one is construct the likelihood function, or rather the log likelihood function. So construct the log likelihood function. So
Sir,
in this
like,
case, my
is it
logarithm of L, now the parameter was theta there, but here no longer my parameter is theta. So this theta would be replaced by tau. So this is the unknown parameter that I'm trying to estimate here. And that would be simply summation over I equals 1 to 10. In general, it will be n, but in this case, it is 10, remember. This is ln, the function of ti given tau. Okay. So this distribution function. Now, if ti tau is again well known, so it comes from here. So this is my f t tau. So if I substitute that over there, so then this thing will be summation over I. Okay. Then log of 1 over tau minus ti over tau. So basically, I am taking the logarithm of the exponential function. I'm taking natural logarithm, but it doesn't matter. All right. So now the next step, so I have constructed my likelihood function, and then comes my step 2, which is maximize the log likelihood. So step 2 is maximize ln L tau, and uh, extract tau hat maximum likelihood. Okay. So this is again my step 2. So I do that explicitly. So I have calculated my log likelihood here. Okay. So this is then del ln L tau del tau. So that I have to calculate. So again, I am copying from my notebooks here. So you should check this very carefully then. So this is summation over I. If I have calculated correctly, this is minus 1 over tau plus ti over tau square. Okay, and so this should be 0 at tau equals tau ml. So this should vanish at tau equals tau at ml. Okay. So what I have here is that, so this gives me the power to write summation over I 1 by 1 over tau ml hat plus ti over tau ml hat square equals to 0. So I replace tau with tau hat ml, and I have that. So now if I simplify that thing, basically, so so this thing summed over I give me n. So this sum is minus n by tau hat ml. The first sum is this. This is the sum, and then plus you have summation over ti, of course, and then tau ml hat square equals 0, and again you simplify, and that is tau ml hat is 1 over n summation over I ti. Okay. So that is the your maximum likelihood estimate for tau. Okay. So this is the ml estimate for tau. Now, a few things are in order. So few comments are in order. So as you can see, this is the arithmetic average of these t's. Now, this is what you should expect, right? Because now for the exponential distribution, this tau is nothing but the average for the exponential distribution, right? The expectation. And as I told you, a good estimator for the average of any distribution, irrespective of it is exponential or it is Gaussian or whatever, is just the arithmetic average. All right. So then you basically, and you have also noticed that this estimator is an unbiased estimator as well. In this case, the maximum likelihood estimator gives me an unbiased estimator, which is a good thing, but it is not always true, by the way. So the thing is, then you have 10 values of this TI, you add them up, you divide by 10, and you get your ML estimate for tau. So if God gave you 5 microsecond, you might get, let's say, 5.05, very close to this, this value. Okay, and you will converge to this God's value that was in God's mind in the limit when your sample size is at infinity. Okay, now if you want to visualize this thing again, so this log likelihood function that you have taken, okay, so this log likelihood function that you had taken, so this ti, these TIs are known numbers, right, that you have measured in an experiment. So that means you have observed your radium nuclei to decay. So this is a function of tau only as well. So again, if you look back at this plot, so here theta plays the role of tau, and here you plot tau, and at some here you will see that it is a maximum. It is a maximum over here, and this will correspond to your tau hat ml, and that is precisely this value over here. Okay.
Sir, that means this tau hat ml is the mean of this all TIs.
Yes, in this case it is, because my distribution here tau is the mean. This is the nature of the
Okay, okay.
exponential
Yeah,
distribution.
yeah, yeah. Okay, sir. Okay.
All right. Now there are certain advantages of using a maximum likelihood estimator. Okay, so remember, this is an estimator I obtained by using the method of maximum likelihood. Okay. Now, why do I do that? Why do we prefer so much this kind of method? Because the maximum likelihood estimates are kind of insensitive to transformation of variable. Okay. Now, what I mean by that, suppose someone was not interested in the lifetime, but they were interested in the decay width, or rather, let's say decay constant, which is the lambda equals 1 over tau. Now, if my tau hat ml, if I know tau hat ml, can I get lambda hat ml very simply? Okay. So if we know tau hat ml, can uh, we obtain lambda hat ml very simply? That is the question I asked. The answer is yes. Now, in general, what you are doing? You are doing, suppose if you are trying to find the estimate for a parameter that I call theta. So what you are using is del theta, okay, or rather, let's say del L del theta equals 0. And from here, you are getting, so this gives you theta hat m. All right. Now, suppose you are not interested in this theta. So you define a variable of your choice, let's say a, which is a function of theta. Okay. And you now say, what is the best estimate for this a? Then one obvious thing to do will be that you change all your distribution function, all your PDFs, not in terms of theta, but in terms of a, and then construct the likelihood function and express the likelihood function in terms of a. And now then, now you do del L del a equals 0, and you get your AML. Okay, but for maximum likelihood, this is not necessary. So what you can easily check is that if I try to do, let's say, del L del a equals 0, then this del a del L is nothing but del L del theta times del theta del a, okay, for a single variable, but for multiple variables as well. Now, if I uh, if I say that this del L del theta equals 0 because of this, then I automatically ensure that del L del A is 0 as well. So I do not have to redo this whole likelihood exercise to get a value of A, that my old parameter theta. Okay. So if I get my my theta ml, then I can just substitute that theta ml into here, and I get my AML. So what I am suggesting is that this a hat ml would be just the function where you have substituted your theta hat ml. This is one note of caution is that if the maximum likelihood estimator, let's say, was an unbiased estimator for theta, it will no longer guarantee this that a hat ml will still be an unbiased estimator for a as well. Okay, so those properties, like say bias and variances, are not preserved by this variable transformation. But as long as the best fit value is concerned, those are quite simply obtained in this scenario. Now, I will do one last thing before going into the practical this thing. So I will ask you, one of you, to share your screen and open any code and follow the instructions, and then we will do a practical how to see these things in reality. So now is the statistical error of uh, ml estimates. Now, what do I mean by that? Okay. Again, if you remember the previous class, this suppose you are trying to estimate this tau ml, and you have 10 data points, these 10 data points, and you give an estimate for this tau hat ml. That is your estimate, that is fine. But somebody, let's say a friend of yours, that person repeats the experiment again, and he or she gets another 10 values of this T1, T2, T3. Those will be, of course, be different. 10 different radium nucleus are decaying now. And this tau hat ml of you and your friend can be different because those are two different experiments. Okay. So if you quote this estimate, let's say 5.05 microsecond, that does not give you the entire information about the reproducibility of the experiment. Okay. Now, this value should be believed with a certain degree of tolerance, and we have to quantify that. Okay. Now, so the precise question is that if I am to repeat this experiment that you have done, and I am again going to get my maximum likelihood estimates, of course I will get a different numerical value that will be different from yours. But I want to quantify how different my value can be from your quoted value, or how strongly should I trust on your quoted value. So that thing will be given by the statistical error of my maximum likelihood estimates. Okay. So to put quite simply, we have calculated this again earlier. So this is the variance of this maximum likelihood estimate. Okay. And we already calculated this thing, okay, in the previous class. And this thing, let me check. Not here. Yeah. So this variance of tau maximum likelihood. Remember the variance of this mu was just sigma square over n. Okay. So here, for an exponential distribution, mu and sigma are both tau, right? So for this distribution, mu equals sigma equals tau, if I remember correctly. So since my maximum likelihood estimate is the same as the estimator for the mean, I can readily generalize this. So this will be tau square over n. So in this case, n equals 10, so it will be tau square over 10. Now, here I have a problem. So the problem is that this tau is the true value of my tau, and I never know the true value of the tau, because the true value of tau is only known by God and it's not accessible to me. So that's why, since this is the analytic expression for this v tau ml, it sounds reasonable that if I try to get my estimate for the statistical error for the estimate of tau, so there are two estimates here. So this estimate for the statistical error, so estimate for the variance, that's why this hat is. Remember, this is the actual statistical error of the variance. This is not an estimate. Okay? This is the actual statistical error. Now, the estimate for the statistical error for the variance, let's say at tau ml, will be, if I replace this tau by my maximum likelihood estimate divided by n. Now I can quote this thing. So this is the value I know, and now my variance becomes a number. Okay. Now, so ideally what I want to do, I want to basically reduce the statistical error. So the statistical error, the estimate for the statistical error would be, so the sigma hat tau ml hat would be just the square root of this variance is just tau ml hat over square root of n. Okay. So this is the statistical error. The estimate. This is the estimate for the statistical error. And this is the estimate for the statistical error.
Sir, on the uh, I mean on the right hand side, earlier you had written sigma square by n, right? And
Here, yes,
so that is the true value of the standard. That is the true value of the variance.
yes. There's a
And
true value of the sigma. Yes,
but here you've written tau square.
because sigma and mu are the same for exponential distribution.
Oh, okay, okay, okay.
So this is sigma for tau. All right. So, so this is the estimate of the statistical error. Now notice a couple of things here. So this is this. So this gives you, this basically quantifies the degree of tolerance of your maximum likelihood estimate. The final numerical value that you quote for tau hat maximum likelihood. How strongly should I believe that value? So this statistical error gives you a measure for that, or an idea about how strongly should you trust that value. Now it depends on two things. First of all is tau hat ml, so that the estimate itself. Now this estimate, so you have very little to do with this estimate, because so this is the estimate for the mean lifetime, right? And since God has already fixed the lifetime, every time you so if that is 5 microsecond, this tau ml will be around 5 microsecond, no matter how many times you do. So the reason why it is important is that if you, so it also reduces as square root of n. Okay, as square root of n. That means if you have a larger sample size, you have a lower statistical error. Okay, so instead of measuring, instead of measuring 10 times, if you had measured, let's say, 100 times, then your statistical error would be reduced proportionately, not proportionately, proportionately is square root. So what I mean is that, let's say, instead of taking 10 samples, if you had taken 100 samples, then your statistical error, the ratio of statistical error, would be square root of 100 over 10, that is square root of 10, that is 3. So you can reduce your error 3 times as much just by increasing the sample size. Okay. Now, how to see it visually? And this is the next task. Okay. Now, someone prepare with your codes that so that we can see these things in practice. So as it happens, so this is your best fit, right? And you see how wide this is a measure of your statistical error. As it happens that if you drop from the maximum value of log L theta, so this is, let's say, ln L max by half, and so this level is ln L max minus half. Why there is ln L max minus half, that we will discuss in the upcoming classes in the mid semester. Need to wait for that. But since I know the result, I know this. So, and in the large sample limit, it is approximately a parabola, and you will see that if you drop down here, then it cuts somewhere here. So this distance is a measure of your sigma hat. So that the sigma hat I talked about. So sigma hat of tau ml hat. So this is the measure of the statistical error of this tau hat. Okay. Now, if you have, so suppose this is the likelihood function. This green curve is the likelihood function for n equals 10. So I have 10 number of samples, and this is the likelihood function. Now, if you have 100 samples and you want to draw this diagram, then the maximum will be in the same place around in here. So I have, let's say, it will be much narrower. That means the statistical error, although your best fit value is in the same place, but the statistical error has reduced. You are saying with 68% confidence level, you can say that your your best fit value of your parameter is within this range. Whereas before, you had to say that with 68% confidence level, your parameter was in this range. So you are reducing the uncertainty in your measurement, in your quoted value, just by increasing the number of samples in your data set. And to be practical, if your sample size increases by 10, so that if this is n equals 10 and the yellow line is n equals 100, then you will see that this should have been reduced approximately by 3.2 actually, to be precise. Okay. Now we are going to check this. But before we proceed to check these things, are there any questions? Any questions? All right. So I hope that you have understood this thing. Now we are going to check these things. So how do I check these things? So first of all, you have to do two things. So you have to suppose, so this is what we are going to do, and let me know who can do this thing. So checking the computer. Explicitly check. So generate n, and this n value will be fixed here. So n random points. Following the exponential distribution. Okay. So suppose I tell you that my fx given tau is equals 1 by tau e to the power minus x by tau. And suppose you fix, so you fix, let's say tau equals 7. So you play the role of God. Okay, so you know that this tau equals 7. And following this distribution, in case 1, you take n equals 10, that is generate 10 random points and save it as a leads. That follows this distribution of tau equals 7. So n equals 10, and that follows tau equals 7. So you will get values like 6.3, 9, 2.9, and so on, 10 values. And case 2, you do n equals 100 as well, as I told you. Again, following tau equals 7. So now you have 100 random points. You have a second vector. Okay. So now you have this as well as this. 100 random points that will be here. So now you see, so once tau equals 7 is given, so that suppose God had given you, now you are looking at this data. So somebody looking at this data, that person doesn't have any idea what is the value of tau. So he just sees this data. Now given this data, he has to guess the value of tau which generated this data. Okay. So how does he guesses it? So he constructs the log likelihood function here, or ln L tau here, the way I told you, and then ln L tau here. And you plot against tau. And you see that this plot is maximum around, let's say, tau equals 7, around tau equals 7. And you also check that if you draw this line of ln L tau max minus half here, so this width in the first case, this width is much larger than the width here, n equals 100. Okay. So, and you compare these things with these analytical values that we have got here. Yeah. And we will do that. So can anyone volunteer at least to do these things right now? Anyone?
How would we get the function L, the likelihood function by multiplying this
How will you
probability
get the
distribution?
likelihood function?
Yeah,
The likelihood function would be just because you know the distribution. You do not know that value of tau, but you know the distribution, right?
I just multiply this 10 times or 100 times.
Yeah, you just multiply this 10 times and you get the likelihood function. But take the log likelihood, like this thing.
Okay.
Okay. Because the likelihood function will be very tricky to deal with. Okay. So can you do this?
Yeah, I can try.
Okay, so open Mathematica and share your screen maybe. Okay, so you understood the problem, right?
Mhm.
Okay, so I will
Mhm.
I will stop sharing.
Okay. Okay, so
Uh, Other people can actually ask questions and suggest for any improvements if they detect something.
yeah, so I guess this is the formula to this is the function which I used to. This is how I would distribute this function. So
You use the exponential distribution.
oh, all right, okay, that's already there, I guess.
Yeah, yeah.
Exponential distribution. Okay.
I think you have to input the parameter like the tau as well. So, what is the structure of the exponential distribution? I do not know.
Yeah, I'll check.
So, you go to Mathematica help and check what is the meaning of the exponential distribution.
Lambda.
I think it is so lambda should be 1 over tau, right? Because the way I had written the distribution,
This is the formula.
yes, lambda times e to the power x by lambda. So
Yeah.
you take lambda equals 1 by 7, so that your tau becomes 7,
Okay.
right? You
Okay.
understand?
Yeah. Okay. So I need to. Yeah.
Yeah, and you save this as a list.
Yeah. So later on. Okay.
Okay. Now, if you see, now before doing anything, if you just want to check your analytic formula, so the analytic formula tells you that the best fit value or the maximum likelihood best fit would be just, in the first case, it will be just the sum of the entries divided by 10, and in the second case, it will be sum of the entries divided by 100. So first check that and see if you get a value close to 10. Yeah. All right. Now you see, these are very different, right? But these are two different experiments, by the way. Not so one is 10 with one is 100. Now, what are the statistical errors in those two? So the statistical errors are these estimates squared by square root of n, right? So in the first case, the statistical error is 8.9119 divided by square root of 10. So you give that a name. Everything you give that a name. So you call it ML1, maximum likelihood estimate.
Okay.
And this is ML2.
Yes.
So now your sigma 1, sigma ML1 rather, is just ML1 divided by square root of 10, right?
Hmm.
It's control to, yeah. See, so now you notice. So in the first case, when you quote your values, you have to quote this 8.91, basically 8.91 plus minus 2.82, right?
Yeah.
Now you see your true value, which is 7, actually lies within this range, right? So you are quoting 8.91 plus minus 2.82.
Hmm.
Okay, and your true value lies within this range, which is a good thing because this is my 1 sigma range, and with for 68% of the time, my true value will lie within that range. Okay, that's my interpretation of sigma in a naive way. And the true value 7 lies within the range from 8 minus 2.82 to 8 plus 2.82. Is that true? You understand that?
Yeah. Yes.
And in the second case, you are quoting the range 6.92 plus minus 0.69.
Yeah.
In the
Okay.
second case also, the true value 7 lies within that range. Okay. But in the second case, your range is very narrow. So you are more confident because you have done more, you have taken more data.
Yeah.
Okay. So this is the thing. Now, since this was a simple case, we could do everything basically analytically. That's what I did. Now, for a more complicated scenario, when this kind of analytical handling is not possible, you have to say this is the only way, this computation is the only way to get your estimates. All right. So and this is done by Monte Carlo. So what Anugrah is doing is that he is simulating data. So what in my example I gave you a kind of in a theoretical way the decay of a radioactive nucleus. Okay, and since I could capture the decay law of the radioactive nucleus by a nice analytic formula, I could do everything analytically. Okay, now, if I did not have the luxury of having the decay formula as a nice analytic form, the only thing I can rely on is Monte Carlo to simulate the decay. So, without actually observing a radium nucleus, what happens? So, I use my computer to simulate the decay of a radium nucleus. And that's what we are doing here. We are simulating the decay, the exponential decay of a radioactive nucleus. Okay? And this would be the only way when we cannot do analytic things. Okay. So is that understood by everyone? So this is a simulation. What we are doing is a simulation, basically. It's the simplest version of a simulation.
Yes.
Yeah. Okay. Good. So now you construct the log likelihood function for the case 1 and case 2 using the analytic formula in this case.
Okay.
So log likelihood, did anyone write down the formula?
It is summation over I log 1 by tau minus ti by tau.
Yeah, exactly.
That-
And those TIs will be the entries of those.
Yeah, so
You have to construct that.
how will I include this? Okay, so I can do it one by one. So ln, okay, natural log, okay, I guess log is log BC, right?
Yeah.
Okay, so log 1 by, so tau I'll have to introduce something called tau here, right?
Right, yeah. Tau is an unknown thing. You have to define a function. So you call it some LL1 function of tau.
I think because I am using this list, I have to do it probably um, like this. So T1 by uh, so yes, is that true? That's correct. Minus T1 by tau plus log 1 by tau. I think this is the way I can do it.
But you have to sum these things, right?
Yeah, so I can just do total. To get this.
Yeah, there should be a more efficient way for that, but maybe. Yeah, and you define it as a function of tau. So you call it LL1 on top. Wait a
Okay.
minute, before total.
So I'll just take out this function from there and
What do you mean? You have already defined it, right?
but can I just directly assign this as a function of
Yeah, I think you should. I think you should be able to do that. Call it L1
L1 as a
first bracket,
function
third bracket start, tau underscore,
underscore
bracket
and
close,
then,
colon equals.
yeah.
Yeah, and yeah, you should put a semicolon so that.
So I think it worked. Right.
Uh,
Um,
yeah,
I
it
mean,
should work, but put a semicolon and then.
so just to be more explicit, shall I just um, define it using the value I got here?
No, 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 no. You have to be you have to be automatized.
Oh,
You
okay then.
so you try to keep things as general as possible.
Okay. Okay, so that's done. So now I have to maximize this.
Now you have to also define L2.
Okay, yeah. Okay.
Okay. Now plot them in the uh, mm, in a plot them in two different plots actually, because those two log likelihoods will have
Okay.
same maximum, but just try to see that one is much narrower than the other.
So from 0 to 10.
10 might be two things. Do 15.
10 is enough, right?
No, 10 is not enough. It's 15. Do it 15.
I guess something's wrong with the definition.
You have to give the argument of L1 in the plot function. L1 tau.
Okay.
I think so.
Yeah. Okay.
Yeah. See, the maxima is not very visible here from this plot. It's around flat, and that is the reason. So try to locate the maxima.
Uh, how do I do that?
I do not know if there is a mathematical function.
Mm.
And do the same for L2.
L2, yeah.
You see, now maybe you can scale it a bit, and so basically in the same plot, actually do this thing. So in the same, so you in the plot L1 over tau, you
Mm.
can do plot L2 tau over 10, let's say. I should not do 10 anyway. Okay, so now what you should do is that try to get the maximum. So you have to put a horizontal line at the maximum of L1 tau and L1 tau minus half. You see, so half would be very small, right? L1 tau minus half would be very small, and it will cut this blue line into two lines. Okay, and you have to draw vertical lines from those two. And in the second plot as well, so here the peak is at 300. So try to find maximum, and on the same plot, basically say that the maximum of L2, you just find there is a maximum function, the maximum of L2, where it occurs, uh, and again draw a maximum line.
Maximum function. Okay, so maximize.
Yeah, so maximize, you say maximize L1 tau. Do the find maximum program. Mm, Copy the second function maybe.
This one.
Yeah. Does it give anything?
Um,
Yeah. So the maximum value is at minus 31 point.
yes, and the tau equal to right. So then I would need to plot.
No, you can also do in the same function. You can do these things. Um, Place put backspace there. You do not need to use so.
Okay,
In this, you do not need to use so.
okay.
So plot L1 tau, okay,
Mm-hmm.
and put L1 tau within a curly bracket.
All right.
Place a comma after L1 tau,
All
and
right.
then put this value minus 31.87. And so what happens? Yeah,
Yes.
see. So this is the now. Now you subtract zero point 0.5 from there.
Mm.
Just put comma again. Yeah. So now you can quote the values basically. So this is the typical things that we quote. So you see that. So you can put two vertical lines from this green lines where you intersect. Okay. So so this is the so it is so the range is from so the best fit value is around 8.1 or something, and the range is from let's say 6 to 13. Okay, so it's a kind of very bad measurement. Okay,
Yeah.
and do the same thing for the other.
Okay.
So now you basically see it's much narrower. Maybe change the range of tau from 0 to 15 to maybe 5 to 10, or rather 6 to 8. You can have better visibility. Yeah. So you can now see that the best fit value is there, and that is much narrower. Okay. And so the larger is your sample size. So remember this maximum likelihood estimator. There is a theorem that I'm not going to prove, by the way, in this class. So the maximum likelihood estimator becomes a Gaussian distributed variable in the limit n tends to infinity. So as n is large, then the maximum likelihood estimator will follow a Gaussian distribution. And the Gaussian distribution will have symmetric error. So you see that in the limit n equals 100, the error is almost symmetric, contrary to the n equals 10 case. So n is not large enough to make the estimator Gaussian distributed. Okay, so you kind of have an asymmetric error there. And so basically, it is also true that if your maximum likelihood thing, if your likelihood function is a Gaussian distribution, then the logarithm of the likelihood function will be an exponential, or rather a parabolic distribution. It's y equals x minus mu whole square. Okay. So you have a visual demonstration of what maximum likelihood can do. Now, a straightforward step from here will be to do the same thing with, let's say, 2 parameters or even more parameters. So one example will be, suppose the same exercise that you did, you do it for Gaussian distribution. Suppose you generate your random variables. Again, you generate a sample of 20. Not now, Anubhav, let me give you. So this is your homework exercise. So you basically simulate two-dimensional data points. So the first one again contains 10 or 20 data points following a Gaussian distribution with a given mu and sigma. So you decide on a mu and sigma. Suppose mu equals 5 and sigma equals 0.5. You decide on that. And you basically generate random numbers following that Gaussian distribution. And following the same Gaussian distribution, you generate 100 such thing. Now you construct the likelihood function and the log likelihood function. Maximize it. It's a two-variable function. So you have like on one axis you have mu, another axis you have sigma. So at some value of mu and sigma, this will have maximum. So in that mu sigma plane, you mark that with a point. That is your best fit value. Okay. And around that point, so it should be a three-dimensional plot, right? Suppose on the x-axis you have mu, on y-axis you have sigma, and on z-axis you have your log likelihood. So it's a three-dimensional plot. So it's like a mountain. So wherever you see the peak of the mountain, the base of that peak, okay, in the mu sigma plane gives you the best fit value for mu and sigma. Hopefully you can all visualize what I'm visualizing here. And around that best fit point, you draw a contour on which the logarithm of the likelihood function drops by 0.5, by half. Okay, and that is your 1 sigma confidence region in the mu sigma plane. Okay, and you try to see if the true value of mu and sigma, using which you generated your Gaussian random points, you simulated this data, they lie within this parabolic shape, or within this this contour of 1 sigma. Okay. So, does everyone understand this exercise? Can you do this?
Yes, sir.
Yeah. So you do this, and we will then meet after the mid semester, and we will start from this likelihood analysis and take it from here, and we'll learn some more things. But hopefully you understood this likelihood things. Okay. Any other questions before I close this session?
Just how we got this 0.5.
Yeah, that will be discussed after mid semester.
Okay. Okay.
Yeah. That is only true when n is large. That's why you see that when n is small, it gives a bad approximation for the standard deviation. But anyway, that's what we. Yeah.
Okay. Okay.
Any other questions? Okay then. So then I will stop recording. And